So today, continuing of course in the at-home videos with my little blackboard, I want to do something a little bit different, which is to talk about geometry. And specifically, I want to talk about the area of a hexagon. What is the area of a hexagon? So the first thing I want to do is label the center of the hexagon and draw a line out to one of the vertices here, and we'll call that distance r. And this is useful because actually if I repeat this process, if I draw a bunch of these lines out to the vertices of the hexagon, then what I can see is that the hexagon is actually made up of 6 triangles. So if I take one of these triangles and kind of blow it up, draw a little bit of a bigger picture of it, then what I can see is that the area of a hexagon is 6 times the area of this triangle that I drew. This bigger version of this one. So it's 6 times the area of this triangle. So if I can figure out the area of the triangle, I'll be done. Now, how can I figure out the area of the triangle? Well, one thing to notice is that this angle here, is exactly 360 degrees divided by 6, because I'm dividing the full circle here into 6 equal pieces. This is a regular hexagon, so everything is symmetric, 6 equal pieces, so that's 60 degrees. So this angle is 60 degrees. But these two angles down here have to be equal to each other by the symmetry of the situation, and the sum of the internal angles of a triangle, as I've shown in another video, is always 180. So if this is 60, and these two are equal, and the sum has to be 180, I'll leave it for you to check for yourselves that these two angles also need to be 60 degrees. So actually this is an equilateral triangle. The hexagon is made up of 6 equilateral triangles. Now we still need to get the area of this triangle. And we know that the area of any triangle is half the base, which is r because it's an equilateral triangle, times the height. We'll call that h. So since the area of this triangle is half the base times the height, half rh, that means that the area of the hexagon is 6 times that, which is 3rh. Now, this is correct, but it's not very satisfying because it's telling me the area of the hexagon in terms of 2 numbers. One is the distance from the center to a vertex, and the other is this h number, which is like the distance from the center to one of the sides. And we can do better than that. We can get the area of a hexagon just in terms of r. And that's where trigonometry comes into play. So how are we going to do that? Well, first of all, we have a right angle triangle here. Now that I've dropped this h line down, we have a right angle triangle. So maybe it's not surprising that trigonometry is going to come into play. Let me remind you of the key fact that we're going to use, which is that the cosine of 60 degrees, or rather actually I'm going to use the sine of 60 degrees, is equal to the square root of 3 over 2. Now, if this looks foreign to you, then go and look at my videos on trigonometry. I have a video specifically where I calculate this value. So we know that the sine of 60 degrees is root 3 over 2. But we also know that the sine of any angle, but of 60 degrees in particular, sine is always opposite over hypotenuse. And we have a right angle triangle right here with an angle of 60 degrees, where the opposite side is h, and the hypotenuse side is r. So if sine of 60 degrees is opposite over hypotenuse, which we can see is h over r, but the sine of 60 degrees is also equal to the square root of 3 over 2, which I've shown in general, that's what sine is equal to, then this implies that square root of 3 over 2 is equal to h over r, which means that h is equal to the square root of 3 times r over 2. And that's very useful because it means, let's just separate this off, that this expression up here for the area of a hexagon can be rewritten as 3r times h which is the square root of 3 times r over 2, which is equal to 3 root 3 r squared over 2. So we have an expression for the area of a hexagon just involving this number r, which is the distance from the center to a vertex, and which is the same as the side length of the hexagon, because these are all equilateral triangles.